Good morning, dear colleagues, dear participants of IT&T conference. It's a great pleasure that the organizing committee could find a way to organize this conference in spite of all the circumstances due to COVID and all other stuff. And it's a great pleasure for me to give a talk on this online part of IT&T conference. My name is Andrey Kuznetsov. I'm an associate professor at the Department of Geoinformatics and Information Security in Samara National Research University. And today my report will be on deep learning approach in remote sensing data forgery detection. Actually, the task of forgery detection is quite modern. It appeared in 2010 or something like this, and now a lot of papers, a lot of research is done in this field. Mainly, the algorithms are developed in a classic pipeline, in a classic approach, where you analyze every image in a sliding window and calculate some local features, which you can use further to analyze the information on an image. So let's get back to the forgery as itself. Forgery is just a type of modification when some intruder or some user with malicious intent would like to embed some changes in the content of an image or video or other digital source. And actually, it is quite hard for an expert using visual analysis to find out what changes have been made in an image. So today we will speak about detection of two main types of changes that can be done, that can be made with an image by someone. Here you can see an example of a remote sensing image where a number of planes on some military base were removed. So if someone receives this image, he can get not correct information about the position of forces, for example, on an image. And the main pipeline of solution that I would like to discuss today and to show you is based on using convolutional neural networks. They are used just to combine all the information in a local area to provide some local features that can be calculated further to detect these two types of forgeries that are shown on an image on the slide. So JPEG images, splicing detection, and Copymove detection. So on the images to the right side, you can see an example of Copymove detection when some part of an image is copied and pasted in another part of an image. So we will speak about train and test set generation and the algorithm itself. And further we will proceed to conclusion, and I will speak about some problems that appear during this research. So if we speak about forgeries as a type of changes that can be done with an image, here you can see several examples. Several soldiers in the center. You can see that these two pictures are different in one soldier. And this soldier is replaced with a background or grass that is also situated on this picture. Another quite often used approach to create forgeries is splicing, when you take some part of an image and embed it or paste it in another image. So when we take two different images, they are usually created in different light conditions and so on. So when you combine them, different visual artifacts can appear. So it is a good way to find out if something has been done with an image. So just a simple example of how one image is translated or is converted to another composite image. So here is an example in the center of the slide. Local temperate regions are usually different from a container image because of different lighting conditions, as I already said, because of compression quality when we combine several JPEG images, for example, different additive noise, or even camera-based properties. All these changes, all these qualities of an image or characteristics of an image, they are um, uh, they lead to different source, different image pixel values or different image characteristics. So these characteristics can be estimated using any algorithm of local features extraction. And in this paper, I'm going to speak about convolutional neural networks as a type of algorithms that can be used for local features extraction. So first I will speak about splicing detection. The main task for this part of a problem was to create image sample dataset for two classes, non-temperate regions and temperate regions. Tempering is a type of embedding changes in an image. Further, we calculate discrete cosine transform coefficients histogram for two-dimensional features using the selected convolutional neural network architecture. We train the model on these features and calculate some local features. Then using this trained neural network, we can estimate the regions. We can try to detect the regions that were tempered, that were changed by someone for the whole input image. The analysis is usually provided in a sliding window to predict the class for every window position. This is quite an ordinary technique for image processing, but when we speak about remote sensing data which have quite a high resolution, this technique leads to some speed decrease, and it's very hard to use it actually. So this is one of the problems that is under construction, is under resolving now. When we speak about discrete cosine transform coefficients histogram calculation, we mean the following algorithm. So first we define the coefficients table. It's the same step as in JPEG algorithm. Then we apply this coefficients for every part of an image and calculate histograms with k-bins of the output image that corresponds to the L part of an applied CT coefficients. So on these two pictures we can see the difference in non-compressed area histogram and compressed area histogram. Here you can see that the structure of this feature is different for compressed and non-compressed area. And using this information we can train our neural network with quite a simple architecture just to differentiate these local blocks on an output image. As I said, the architecture is quite simple. So we have several convolutional layers. The first one with 64 filters, then two convolutional layers also with 64 filters. The dense layer with 512 elements, and then dense output layer with 2 elements with a softmax activation function for us to receive the result output on making some prediction on a window part of the image that we will analyze. If we come back to the list of forgery types, the second one is Copymove detection. For this task, we created two procedures, training and validation. On the training scheme, we can see the following steps. So we take some training set of local blocks of an image, of a remote sensing images, and even ordinary images, because in most parts they are not different. In most tasks they are not different mostly, because most of them have 3 channels, and the main difference uh, is in resolution. Then we extract some features, select them, and train classification algorithm to find, for example, similar features, which can be a result of embedding a duplicate or a Copymove block. On the validation set, we do the following. We extract the features, apply classification algorithm, and give some output result of Copymove detection. As I've said, for remote sensing data, we have some processing limits. It's high resolution. These images can contain more than 3 channels. Then we need to retrain our network or fine-tune it for this type of data. And another special type of data is radar data. These tasks need to be solved, and this is a very interesting task for the research. It's quite a challenging task. Speaking about the CNN model that was used for Copymove detection or for feature extraction in the Copymove detection task, here is the architecture that was used to create the output 64 dimensional features for every local part of an image in a sliding window mode. So the input layer contains m by n by 3 pixels, and then the description of all the layers is also presented on this slide. It's quite usual, quite a simple convolutional neural network. Speaking about the dataset creation for experiments, I used quite usually used Cassia V2 dataset, which is usually used in experiments and in research on Copymove detection and on splicing detection. This would be good for comparison with other researchers. And added several Landsat images just to be sure that we will not miss some features that are that are specific for remote sensing data as a type of data. So then we divide images into blocks, apply JPEG compression with different quality. This is done for the first task because for the task of Copymove detection, it is not important for us to know information about preprocessing, because we think that, and we suppose that features should be trained for Copymove detection task without any information about what processing has been done. So it is more general task. And during the training stage, we first freeze all the layers except classification layer, if we speak about splicing detection, and then unfreeze all the layers for fine-tuning the features. As initial weights, we used ImageNet weights because they are quite usually used in different architectures. These weights were taken from ResNet architecture. For feature extraction in Copymove detection task, the proposed network architecture was trained from scratch. And here you can see the result of training for splicing detection. Speaking about the results of experiments, we provide here several results. For splicing detection, this is a comparison of 3 algorithms. Um, the links are presented in the paper, and you can find more information about the algorithms used here. But you can see that deep learning approach, which is in the middle column, it provides quite better results, a little bit, but still it provides better results for splicing detection. For Copymove detection results, you can see that the developed approach based on calculation of local features in sliding window using a deep convolutional network provides better results using the metric F1 score, and precision and recall values are also higher for most of the parts. Speaking about the validation dataset, it was a part of a combination of KSA-V2 dataset and several Landsat images. And here you can see the results on some images from KSA dataset and from Landsat images. You can see that on the half-tone image, 2 duplicates or 2 Copymove regions were detected. On the RGB images from KSA-V2 dataset, you can also see the result of splicing detection and the result of Copymove detection. Moving forward to conclusions and to results, we can see that the proposed patch-based splicing detection algorithm and Copymove feature extraction solution are quite applicable and quite well used for these current tasks. The CNN architectures are quite simple, so they can be used anyway on every machine, because the trained models take several megabytes in size on the hard drive. The problem in computational complexity still exists, and it needs to be decreased because sliding window mode is quite slow, and this problem makes some difficulties for remote sensing data analysis. And here are some research questions that I ask myself when thinking forward about future research. So what if we want to detect JPEG compressed fragments in a compressed image with a different quality factor, if we speak about splicing detection? Also, another question on compression is double compression. And feature comparison time should be increased, and maybe autoencoders techniques can be used to compare patches in latent space, but this is a research question for future. Thank you very much for your attention. I would be glad to answer your questions or make some comments on what I have just talked about. Thank you very much for your attention. Goodbye.